Hello, I'm Youngbom Kim from Dongguk University DTM Lab. Today I'm going to review a paper titled Technology Convergence Prediction based on temporal heterogeneous graph neural networks. This slide presents the bibliographic information of the paper. The study was published in Information Processing and Management in 2025 and proposes a temporal heterogeneous graph neural network model called THGNN-TCP. The main keywords include technology convergence, temporal heterogeneous graph neural networks, link prediction, metapaths, technology opportunity, discovery, and LSTM. In terms of highlights, the model integrates patents, scientific papers, and IPC codes to predict technology convergence. It uses metapath-based learning and LSTM to capture structure, semantic, and temporal technology relationships. The proposed model also outperforms baseline methods and identifies convergence opportunities at multiple levels of IPC hierarchy. Here are the contents of today's review. Here is the research background. Identifying emerging technology trends and opportunities is essential for firms seeking to maintain long-term competitiveness. Early identification allows firms to enter new markets, establish strategic advantages, and respond more effectively to technological change. Technology convergence occurs when different technological fields are combined to create new functions, products, and markets. While this convergence can generate new business opportunities, it may also disrupt existing value chains and challenge incumbent firms. Patent data are widely used to identify technology convergence opportunities because they contain detailed information on inventions and knowledge relationships. Previous studies have therefore applied patent mapping, network analysis, text mining, and link prediction. Among these approaches, graph neural networks are especially useful because they can learn technology representations while preserving complex network structures. They also support link prediction by estimating future relationships between previously unconnected technology nodes. Previous studies mainly predicted technology convergence through the co-occurrence of technological elements. However, they often overlooked semantic distance, knowledge flow, and the dynamic evolution of technology relationships. Most studies have also relied mainly on patent data, which limits their ability to capture interactions between science and technology. Scientific papers provide important knowledge inputs for technological development, but few studies have jointly modeled papers, patents, and fine-grained IPC codes in a dynamic heterogeneous network. To address these limitations, the study proposes THGNN-TCP, metapath-based GNNs capture structure and semantic features, while LSTM learns temporal dependencies to identify future technology convergence opportunities at multiple IPC levels. Here's the literature on technology opportunity analysis. Technology opportunities refer to possibilities for technological advancement that arise from scientific progress, technologies developed in other fields, and feedback from existing industries. Previous studies have interpreted these opportunities in several ways, including unexplored technological areas, rapidly emerging technologies, and new combinations of previously separated technologies. Patent classification codes and keywords are commonly used to represent technology fields. Based on this data, researchers have applied methods such as morphological analysis, patent mapping, outlier detection, SAO-based semantic mining, and network analysis. More recent studies have also begun to incorporate multi-source data to overcome the limitations of relying on patent information. Next, the literature focuses on technology convergence prediction and graph representation learning. Technology convergence refers to combining two or more existing technologies into a new hybrid technology. Previous studies have mainly identified convergence through technological co-occurrence and citation relationships. Co-occurrence indicates that technologies are used together, while citations represent knowledge flows between them. Existing approaches include link prediction and indicator-based methods. However, many of them rely heavily on patent co-occurrence and do not sufficiently capture semantic relationships or interactions between science and technology. GNN can learn node representations while preserving complex network structures. Heterogeneous graph and meta paths further represent multiple node types and their structure and semantic relationships. However, existing methods often overlook differences in node importance and interactions among attention heads. Therefore, this study adopts a metapath-based temporal heterogeneous GNN to capture both heterogeneous technology relationships and their temporal evolution. Here are the research objectives. The first objective is to construct a dynamic technology convergence prediction model using patents and scientific papers. The model considers technology co-occurrence, semantic distance, knowledge flow, and science-technology linkages, while also capturing changes in technological relationships over time. The second objective is to identify technology convergence opportunities from a multi-level perspective. The study used the lowest level IPC codes to represent fine-grained technologies and analyze opportunities based on the hierarchical structure of the IPC system. Overall, the proposed framework integrates structure, semantic, and temporal information to support fine-grained technology convergence analysis and research decision-making. This is the overall research process. The THGNN-TCP framework consists of 5 stages. First, patents, cited papers, and patent classification information are collected and pre-processed. Second, temporal heterogeneous networks are constructed using classification number, patent, and paper nodes. Third, node type specific embeddings are generated from texture, semantic, and external features. Fourth, metapath-based heterogeneous GNNs learns IPC representations for each time period. Finally, LSTM captures temporal changes and link prediction is used to identify previously unobserved technology convergence opportunities. Overall, the framework transforms multi-source data into temporal technology representations for convergence prediction. Here is the multi-source data collection and processing process. The figure shows that the study combines 3 types of data: target patents from global patent databases, cited papers from academic databases, and IPC or CPC information from patent classification systems. These sources are integrated into a single multi-source data set after pre-processing. The search strings and timescope are first defined according to the target technology field. Target patents are collected from databases such as Torrent and Incopet, while cited papers and patents are retrieved from Scopus, Web of Science, and patent databases. Finally, classification codes and their hierarchical information are collected for each year, and the entire dataset is merged, deduplicated, translated when necessary, and filtered to remove patents without usable abstracts. This is the construction of the temporal heterogeneous networks. The patent dataset is first divided into multiple time periods, and a separate heterogeneous network is constructed for each period. As shown in the figure, the network contains 3 node types: classification numbers, patents, and scientific papers. Patent nodes include both patents from the target period and their cited patents, while paper nodes represent scientific papers cited by those patents. 3 metapaths are then used to represent different relationships between technologies. CNPTCN captures direct technology of co-occurrence. CNPTPTCN represents knowledge flow through patent citations, and CNPTPRPTCN captures science to technology knowledge flow. By constructing these network snapshots over time, the model can capture both heterogeneous technology relationships and their temporal changes. Here's the node embedding process. A node type-aware strategy is used to preserve the distinct information of patents, papers, and classification numbers. For patent nodes, titles and abstracts are encoded using sentence BERT. Citation frequency, claim count, and technological advancement are then added, producing a 771-dimensional initial embedding. Paper notes are encoded in the same way using titles and abstracts, with citation frequency added to generate a 769-dimensional embedding. For classification number nodes, IPC nodes are encoded using sentence BERT. In addition, semantic distances between IPC codes are calculated from the hierarchical IPC structures shown in the figure. Finally, MDS converts the distance matrix into semantic vectors, allowing texture and hierarchical information to be combined in the CN embeddings. Here's the metapath-based node representation process. For each target CN node, the model first identifies multiple instances of the predefined metapath. The features on CN, patents, and paper nodes are then aggregated using node type specific weights reflecting their different contributions. Next, Talking Heads attention combines the instance representations within each metapath. An additional linear projection allows information to be exchanged across attention heads. Finally, additive attention integrates the metapath-specific vectors and generates the final representation of the target CN node. The figure summarizes this process from node-type-aware aggregation to the final CN representation. The CN representations learned from each time period network are organized into a time series sequence. Each sequence is then fed into a LSTM to capture the temporal evolution of technology features. The output vector from the final period is used as the dynamic representation of each CN node. Next, cosine similarity is calculated between every pair of CN nodes. Pairs exceeding the similarity threshold are considered potential convergence opportunities. Finally, the predicted CN network is compared with networks from previous periods. As shown in the figure, newly emerging links that did not previously exist are identified as future technology convergence opportunities. Here's the loss function. The model uses binary cross entropy loss to preserve technology co-occurrence relationships in each temporal network snapshot. In the equation, the loss is calculated across all time periods and CN nodes. For positive samples, newly connected CN pairs are encouraged to have similar representations. For negative samples, unconnected CN pairs are pushed far, farther apart. The sigmoid function converts the similarity between node vectors into a probability, while the negative sampling rate balances the larger number of negative samples. Overall, the loss guides the model to distinguish future convergence links from unrelated technology pairs. Here's the dataset and experimental overview. The study focuses on large language model technologies using patent data from INCOPAT and scientific papers from Scopus. The research strategy combined the term language model with representative model names to collect relevant patents. Because the field is developing rapidly, honor time windows were used to construct temporal network snapshots. The final dataset integrates patents, IPC codes, scientific papers, and their co-occurrence and citation relationships as summarized in the table. THGN and TCP was compared with 6 baseline models using EUC, AP, and FON. Only previously unseen IPC co-occurrence links were treated as potential technology convergence opportunities. As shown in the table, THGN and TCP achieved the highest AUC and AP, indicating strong overall link prediction performance. DYZ produced a slightly higher F1 score, but its AUC and AP were lower than those of THGN and TCP. In addition, the relatively low standard deviations show that the proposed model maintains stable performance across repeated experiments. Here are the ablation study results. The first experiment evaluates the contribution of each metapath. As shown in the left table, the complete THGN and TCP model achieved the best performance across all three metrics. Among the three metapaths, CN-PT-CN contributed the most, followed by CN-PT-PT-CN. The science to technology path, CN-PT-PT-CN, had a smaller effect but still provided additional predictive information. The second experiment examines the influence of different node embeddings. Using all three node types produced the best and most stable performance. Among them, classification number embeddings had the greatest influence, followed by patent embeddings. Paper embeddings were relatively less influential, but they still provided complementary information to the model. Here's the parameters sensitivity analysis. The study examined three hyperparameters: the embedding dimension, the LSTM output dimension, and the number of attention heads. As shown in the picture, prediction performance was most sensitive to the LSTM output dimension, followed by the number of attention heads. The embedding dimension had a relatively smaller effect. The best performance was achieved when both the embedding dimension and LSTM output dimension were set to 128 with 8 attention heads. Smaller dimensions limited feature learning, while excessively large dimensions or too many attention heads introduced redundant information and noise. Here are the multi-level convergence results. Using a prediction threshold of 0.85, THGNN-TCP identified 1,403 previously unobserved convergence links. These opportunities were then analyzed across different levels of the IPC hierarchy. At the section level, convergence within section G shows the greatest potential. At the class level, G06 accounted for the largest proportion, while at the subclass level, convergence within G06F was the most prominent. Overall, the predicted opportunities were concentrated mainly in computing and information processing technologies. Here's the empirical validation. The prediction results were validated using new LLM-related patents filed in 2024. These patents were collected using the same search strategy as the original dataset. As of September 18, 2024, 59 predicted technology convergence pairs had already appeared in actual patents. The table presents the top 5 realized convergence pairs at the lowest IPC level. These pairs are mainly related to database construction, personalized service, content processing, privacy protection, and LLM optimization. Overall, the results confirm that the predicted links were later realized as extra technology combinations. Here are the theoretical and practical implications. From a theoretical perspective, the use of lowest level IPC codes enables fine-grained and multi-level technology opportunity prediction. Combining structure and semantic features also improves prediction accuracy and allows the results to be analyzed from different perspectives. The study further expands technology opportunity discovery by applying heterogeneous GNNs to technological innovation research. From a practical perspective, the model supports the early identification of frontier technologies and convergence opportunities. The IPC hierarchy allows these patterns to be examined from macro, meso, and micro perspectives. In addition, IPC-based network visualization improves the interpretation of prediction opportunities and supports technology strategies, R&D planning, and product innovation decisions. Here are the limitations and future research directions. First, the model relies only on patents and scientific papers, while policy, market, product, and industrial data are not considered. Second, all IPC codes are treated equally, although primary and secondary classification codes may represent different levels of technological relevance. The predicted opportunities also require expert knowledge for practical interpretation, which limits the model's interpretability. Future research could incorporate industrial and economic information as additional nodes, apply continuous time dynamic graph models, and develop more intuitive methods for explaining predicted convergence opportunities. Finally, here is the conclusion. The study proposed THGNN-TCP, which integrates patents, scientific papers, and fine-grained IPC codes to predict dynamic technology convergence. Metaphase-based representation learning captures technology co-occurrence, patent citation flows, and science-to-technology knowledge transfer, while LSTM models changes in these relationships over time. The model shows strong prediction performance in the LLM field, and several predicted convergence links were later observed in newly filed patents. Overall, the framework supports multi-level technology opportunity analysis and can contribute to technology forecasting, R&D planning, and innovation decision-making. Thank you for listening my paper review.